Hello and welcome to the RAIC Corporate Affiliate Series. My name is Pamela Burke and I'm the Education Administrator at the RAIC. Our corporate affiliate for today's webinar is Owens Corning. Owens Corning develops, manufactures, and markets insulation, roofing, and fiberglass composites. Global in scope and human scale, the company's market-leading businesses use their deep expertise in materials, manufacturing, and building science to develop products and systems that save energy and improve comfort in commercial and residential buildings. Through its glass reinforcement business, the company makes thousands of products lighter, stronger, and more durable. Ultimately, Owens Corning people and products make the world a better place. Based in Toledo, Ohio, Owens Corning posted 2017 sales of $6.4 billion and employs 19,000 people in 37 countries. It has been a Fortune 500 company for 63 consecutive years. Today's presentation is titled High Performance Wall Enclosure Systems for Commercial Buildings on the Path Towards Net Zero Ready Performance by 2030 and is presented by Salvatore Ciarlo.
Okay, well, good day and welcome to all to this webinar. And today's webinar is on high performance wall enclosure systems for commercial buildings on the path towards net zero ready performance by 2030. So I'm Sal Ciarlo. I'm the Technical Services Director for Owens Corning Canada. And today's learning objectives is understanding the difference in thermal resistance requirements between the National Energy Code for Buildings 2015 and 2017. We'll look at different metal cladding attachment options to help reduce thermal bridging and wall enclosure systems, and at the same time, allow us to meet the new energy efficiency requirements in both the 2015 and the 2017 Energy Code for Buildings. We'll look at some insulation options to meet the new effective thermal resistance requirements and the benefits of split insulated wall assemblies. And then finally, we'll look at some design guides and available tools to help design high performance durable building envelope enclosures. So, what is driving changes in energy efficiency for new buildings across Canada? Well, it's obviously Canada's commitment to clean energy and climate change. So it's part of the pan-Canadian framework. Basically, what Canada is committed to, as I think we all know, is that we want to make sure that we lower our carbon emissions 30% below 2005 levels by 2030. And so how we're going to get there, basically the two principal actions. The first one is making new buildings more energy efficient, which is why we're seeing changes, energy efficiency, updates in energy efficiency requirements in the commercial building code across Canada for new buildings. But also we're going to be looking at, or the federal government is going to be looking at introducing a retrofit code to help make existing buildings more energy efficient so that we can meet our objectives by 2030 and full net zero by 2050. And so basically, in parallel to new energy codes, it is being considered that we make buildings, we label buildings in terms of their energy use to help educate the marketplace so that we can move faster along this path towards net zero ready by 2030. So if we take a look at energy codes for commercial buildings, so basically I'm going to talk to you about two codes that are currently referenced in the energy codes. So there's the ASHRAE 90.1 standard, as well as the NECB National Energy Code of Canada for Buildings, the 2015 and the 2017 edition. These are the two main codes that are referenced, main standards, sorry, that are referenced for energy efficiency across Canada. And there's some provinces that have their specific standards, like the Toronto Green Building Standard, as well as Quebec has their own energy efficiency requirement code. It's a hybrid code between the 2015 and 2017. But I'm just going to talk about the national code for today's webinar. So just quickly, if I look at ASHRAE 90.1, the 2016 and 2019 edition, and if we look at U-value requirements for walls above grade, for steel framed walls, so we can see that for the different climate zones, it gives you prescriptively what the minimum insulation value needs to be, as well as the minimum amount of CI, continuous insulation, on the exterior of those walls. And what's important to remember is that when we see the terminology CI, continuous insulation, it is meant or is intended that the insulation is continuous across all structural members without thermal bridges other than fasteners and service openings. So if you've got like a metal Z-curve or a steel lintel that's going through the insulation, it doesn't meet the prescriptive requirement of the for continuous insulation, because that component is actually going to be a major thermal bridge and short circuit the nominal thermal resistance of the insulation. So it's important you remember that when you see CI, it's intended to be continuous without any interruptions. Now, if I go to the 2015 and 2017 National Energy Code for Buildings for Canada, so basically you can see that, again, we see 6 climate zones. There's a maximum U value and effective R value requirements for the different components of the building envelope by climate zone. We all know that U value is just the inverse of effective thermal resistance, so that's how you get the values. You can see that the values are a little different between the 2015 and the 2017 edition. So depending on what edition is enforced in the province that you're working in, these are the requirements. This is what the requirements look like. So now, what I'm going to talk about is the importance of thermal bridges to meet those effective U value requirements for opaque assemblies. So if we look at the NECB 2015 prescriptive requirements for wall assemblies above grade, so the U value or effective thermal resistance, what needs to be considered is basically the opaque portion with the structure. So let's just say steel studs and all of its components. You need to account for the heat flow through the structure, heat flow through the clear field. If we look at the 2017 edition, there's a further requirement where you now need to account for or include in the calculation of your overall U value for the wall area. You need to include not only the heat flow through the clear field, but also the junctions. So what are some of the junctions that need to be included in the calculation of the U value for the facade, for the opaque area? It's the junctions between the wall and the foundation wall, junction between 2 different walls that have different cladding materials or insulation levels, the junctions between the window openings, let's say, and the opaque wall, the slab edge details or junctions, and then the junction of the wall to the parapet. Because at each one of those junctions, there's going to be heat flow that the NECB 2015 doesn't account for. And in the NECB 2017, you need to account for that. So again, if the U value is the same, in some instances it is for some portions of the assemblies. If it's the same in the NECB 2015 and 2017, you can see that it's a little bit more difficult to achieve the target in the 2017 because you have to include additional heat flow paths through the junctions. So that's a significant change, something you need to be aware of depending on what code you're designing to and that is being enforced in the region that you're working in. So why is it important to address the thermal bridges? So you can see from this study that was done by third-party consultant. So basically, if we take a look at a wood frame assembly with R19 cavity insulation, and then a steel frame structure with R10 exterior insulation and R12 cavity insulation, and then the last building that was looked at is a concrete building with R10 interior insulation. In all 3 cases, you can see the heat flow associated with the clear field, which is in blue, versus the heat flow associated with the details, where it includes the heat flow through the junctions. In all cases, you can see that there is as much, if not more, heat flow associated with the junctions than the heat flow associated with clear field assembly. So if we want to have a true picture of the demand, the energy demand of our building, we need to account for both, especially the portion that has more off, which is basically the heat flow associated with the details. So it's important to be aware of that. Here's an example that I borrowed from the Transform Énergie Quebec, where Quebec has launched a new energy efficiency code for commercial buildings. And if we look at this assembly here, so let's just assume that the assembly is a steel stud wall with cavity insulation, some type of gypsum board, It's exactly the same wall that we're gonna calculate three different ways. So the first way is if we were just to calculate a total R value of the wall assembly. So in some provinces up until now, the energy efficiency requirements, basically the way you had to comply was adding the thermal resistance of all the layers, excluding the heat flow through the structure from air film, outside air film to inside air film. So if you do that, you did that in this example, it would give you a nominal R value for the system of R42. That same exact wall, if we were to apply the NECB 2015 method of calculating effective U value, or effective R value, sorry, where you have to account for the heat flow through the structure, the studs, it would give you an R26. So now we've gone from 42 to 26 effective. And if you were to calculate that same wall, or evaluate that same wall, and use the NECB 2017 method, where not only do you have to account for the heat flow through the structure, but also for all the heat flow through the junctions, that same wall is now R13 effective. So you can see we went from a 42 to a 13. The 13 is really the real value, and that's what we need to migrate to. And we need to. That's why it's important to account for the heat flow not only through the structure but through the junctions, because it's significant, and we need to make sure that we quantify it effectively and address it, so that we minimize heat demand, so that we can help reduce carbon emissions if we're using an energy that is carbon intense. So here's another example of the importance of addressing the thermal bridges. So I'm using a steel stud wall assembly, no insulation in the cavity, gypsum board on the inside, exterior gypsum sheathing on the outside. And I've got different types of connection methods to attach metal cladding to the backup wall with some type of continuous insulation on the exterior. So if I were to put in R20 exterior insulation, so let's just say 4 to 5 inches of mineral wool as an example on the exterior, and I were to glue that onto the gypsum board sheathing without any Z-girds that short circuit the insulation, and then I can calculate the effective thermal resistance of the entire assembly, it would give me an effective R22.7. However, when we start applying Z-girds, so say vertical Z-girds to connect the cladding, metal cladding to the backup wall, you can see that that nominal R20 has now actually has now gone down to R11, and that's because of the thermal bridge that's created by that Z-gird. So now if I were to use horizontal Z-girds, it gets a little better because there's less area of contact where the heat flow goes from inside to outside or vice versa. And so now it gives me an R13.1 effective. And if I use a combination of vertical and horizontal Z-girds, it's R15.4. So you can see that it gets better when I start using better attachment methods. And if I use intermittent Z-girds, depending on the spacing, I can get to as high as an R17.5 effective versus a perfect wall of R22.7 if I had no disruptions or discontinuities through the exterior insulation. You can see here that just by the numbers that the type of cladding attachment is going to have a significant impact on the thickness of insulation and the thickness of the overall wall in order to meet the new effective thermal resistance requirement in the energy code across Canada. So cladding attachments are key. On the screen, you can see kind of what I classify as the good, better, best examples. So basically, standard metal Z-girds are, you can still use them, but it's going to require a significant amount of exterior insulation because it actually lowers the nominal resistance of the insulation because of the major thermal bridge. Better options are, intermittent ties. Even better are thermally isolated clips. And kind of one of the best options that I'm going to talk to you about today is if you can attach the metal cladding directly through the insulation with some hat channels and using long screws, this is going to provide the best overall performance for the wall because it provides the least thermal bridge. And so therefore now you can meet the U value requirements with a thinner insulation on the exterior. So here's an example of a document from RDH that is done, and I'll show you the reference at the end of the presentation. So Basically, if you take a look at the chart here, it kind of tells you, depending on the type of metal cladding attachment that you choose, it gives you the percent insulation effectiveness. So the percent insulation effectiveness of the exterior insulation. So as an example, if I use continuous vertical Z-girds or horizontal Z-girds, on average, it's only going to allow me to retain 40% of the nominal exterior insulation value. So if I put in 4 inches of mineral wool and it gives me or 5 inches of mineral wool that gives me, let's say, a nominal R20, it's actually only going to be, it's only going to be contributing 40% of that R20 in terms of overall U value or effective thermal resistance to that wall assembly. So if I need to get to high levels, such as 20 effective R20 or 23 or 25, I'm going to need a significant amount because of the thermal bridge caused by the girt attachment. If I go to thermally isolated clips, now you can see, because they're less conductive, you can basically retain 80% of the insulation effectiveness, of the exterior insulation effectiveness. So again, if I put on R20, I'm getting R16 out of it, basically in terms of overall contribution to the wall system, which is significant. And if I use long screws to attach the cladding through the insulation, because now I'm minimizing to the maximum the amount of thermal bridge that I have through that insulation, the insulation effectiveness would be 95%. So it's important, again, to choose the most effective one based on your design. And what's also interesting here from that same study is that you can see that when you put more insulation on the exterior, the thermal bridge actually accentuates. So the more insulation you put on the outside, the more degradation you have in terms of its overall percent thermal degradation of the exterior insulation. So it's kind of interesting. I thought I'd share that with you. Now, if we were to consider adding some type of insulation in the backup wall, so here as an example, if we add fiberglass insulation, R20 fiberglass insulation in the backup wall, that R20 nominal R value is actually contributing about an R9 effectively to the overall system. So it's a good contributor, even though I'm only getting an R9 effectively from an R20 nominal value. It still allows me it still yields an R9 contribution in terms of overall effective R value for the system. And now I have much less to make up for on the exterior, so I can probably get to whatever level of performance I'm looking for using thinner thickness of insulation, which means less cost. You don't have to have long fasteners, the length of the cladding attachments. So it can start to add up quite a bit, and it actually allows us to get to the overall thermal resistance requirements in a very effective way. So here's an example. This is coming out of our thermal resistance guide, thermal bridge guide, sorry, that we have online. So here's an example of a steel stud wall, 2x6 steel studs with exterior metal cladding that's attached with intermittent vertical Z-girds. So if I had air in the stud cavity, so no insulation in the stud cavity, with 5 inches of mineral wool on the outside, that is a nominal R21 value, the effective thermal resistance of that assembly would be R17.6 with 5 inches of insulation. So if I'm trying to reach an effective R value of 20 or 23, which is kind of what is required in most of the zones or in the central zones, I don't have enough with 5 inches of mineral wool. I'd have to go to 6, 7, or maybe even 8 inches of mineral wool to meet the requirement. The minute I start to add an insulation in the cavity, so here if I take a look at it, if I add an R20 batt insulation in the cavity, now I meet the effective 20.5 or 23.2 with 3 to 4 inches of exterior insulation. So a lot less thickness required on the exterior in combination with the fiberglass insulation in the cavity gives me a very thin wall and a high performance wall. So this is the advantages of considering a split insulated wall assembly, is that it helps you meet the overall requirements with a thinner wall. Same thing for brick, same example for brick. So if I had a brick cladding with masonry anchors, so you can see that I only get to an effective R17.6 with 5 inches of mineral wool on the outside, or nominal R21. And if I want to get to an effective 20 or 23, all I need, if I add insulation in the cavity on R20, again, all I need is 3 to 4 inches. So typically what we're seeing here is a reduction of 50% in the thickness required on the exterior if I insulate the backup wall with cavity insulation. So it, again, yields a thinner wall, a much more cost-effective wall, and it doesn't, it helps to meet the requirements in a more cost-effective way. So again, the two options really moving forward is to continue doing what we're doing, which they're currently doing, the majority of the provinces are doing, from what we're seeing, is to continue insulating all on the exterior. And so now you've got your control layers, you've got your thermal control layer, you've got your membranes acting as your water and air barrier, as well as your vapor barrier. And then you've got your backup wall that's not insulated. So again, depending on the type of cladding attachments, it's going to dictate the thickness of insulation required. So the more efficient those cladding attachments are, whether it's masonry or metal cladding, the less thickness is going to be required on the exterior to meet the new requirements, the new energy efficiency requirements across Canada. Or the other option is to consider a split insulated wall assembly, where now you're actually insulating the backup wall, the cavity of the backup wall, with fiberglass or mineral wool insulation, and you're putting less thickness of exterior, continuous exterior insulation. Therefore, you're going to need less, the length of your screws get less, the length of your lintels get less, and it adds up. And the only thing that we need to remember is that we're considering this option is that you're typically, if you have a membrane on the outside, a peel and stick membrane or spray applied membrane, it acts now as your moisture barrier, your air barrier, but it cannot be a vapor barrier. So it's got to be vapor open, because the vapor control layer needs to be on the warm side of the insulation, which is in front of the insulation of the backup wall on the warm side of the assembly. So that needs to be, you need to make that adjustment. So I'm going to walk you through an example now of how you can, different options to meet the new energy code effective R values, of either 20.4 or effective 23. And I chose 20.4 because that's the new requirement in the province of Quebec, and 23, it's kind of the requirement for the rest of the provinces for climate zone 6. And so again, here's an example of a 2x6 steel stud wall, 16 inches on center, half-inch gypsum board sheathing on both sides. So if I calculate the effective R value of just that base assembly with no insulation on the outside or on the inside, it gives me R3.1. So I need to get let's use 23 as an example here. So I need to add another R20 effective to meet the requirement. So now if I choose to attach metal cladding with standard Z girds, and I use the table we just saw from the RDH study that tells me that I'm using a regular standard Z gird, the insulation effectiveness is only, let's say, 50% of the nominal R value. Well, I would need 8 to 10 inches of exterior insulation to get to the effective 23. So I can get there, I just need a thick amount. If I were to use thermally isolated clips, and again, based on the chart that was provided by RDH in their study, if we consider that the thermally isolated clips have 75% insulation effectiveness, now I would only need an extra 5.5 to 6.5 of exterior insulation. And what I'm using here in my example is continuous insulation, mineral wool continuous insulation on the exterior as an R value of R4.2 per inch. So again, you can see a significant reduction required in terms of the overall thickness of insulation on the exterior based on the type of cladding attachment used. And if I use the method where I'm attaching the cladding directly through the insulation with long screws, you can see here that again, if we look at the chart that was provided by RDH, this type of attachment method allows us to retain 95% of the insulation thermal resistance for the exterior insulation. So now I would only need like 4.5 to 5 inches thick CI on the exterior to meet effective R23. So again, the thickness is reduced. Now, if I were to add insulation in the cavity, so the minute I add an R20 fiberglass batt in the cavity, that initial value with an empty stud for the backup wall, which was an R3.1, is now gone up to 11.6 in terms of effective thermal resistance. So now I only need to make up the difference between 11.6 and 23 on the exterior. So again, if I choose the Z-bar cladding attachment and apply the insulation effective ratio or percentage that was provided by RDH in their report, I would need 4.5 to 5.5 inches of mineral wool insulation at R4.2 per inch to meet your effective R23. If I choose the thermally isolated clip option, well, it goes down to 3 to 4 inches required on the exterior. And if I attach the cladding with long screws through the insulation, now I only need 2.25 to 3 inches of insulation. So you can clearly see the benefit. If you're adding insulation in the backup wall, you're actually significantly reducing the thickness of the exterior insulation required, regardless of the cladding attachment method. And so the trade-off is significant because it's going to allow you to design a thinner wall, but the cost of the materials is also significant to understand because the insulation in the cavity is giving you the performance it's giving you is at a lower cost than the same performance of the exterior insulation. So again, an opportunity to reduce overall cost and improve overall performance. So some of the options, if considering a split insulated wall assembly, many of the manufacturers out there offer a mineral wool or a glass fiber insulation for both steel studs and wood studs. They're available for 2x4 studs and 2x6 studs. And as an example, in 2x6 studs for the same thickness, what's available in the marketplace is R19, R20, R22, and R24 batts. So basically, the density changes. You get higher thermal performance for the same thickness. And what we recommend is starting with an R20 in the backup wall, and then kind of making sure you meet the overall requirements by adding continuous insulation on the exterior of the wall. So again, what's important to remember is if you're using a standard wall where you're insulating the wall completely on the exterior of the exterior gypsum and no insulation in the cavity of the backup wall, you want to make sure that your membrane, whether it's peel and stick or spray applied, that acts as your moisture barrier and your air barrier, is actually non-permeable. So it's also going to be your vapor barrier if you're insulating outward, all on the outside of that. However, if you consider the split insulated wall assembly, where you're insulating on both sides of the exterior gypsum board, so in the backup wall and in front of that, well, now that membrane or that peel and stick membrane or a spray applied membrane that provides your air barrier and moisture barrier has to now be vapor open. It has to be permeable because your vapor barrier is on the warm side of the insulation on the inside of the building. And so here's an interesting study, and just to highlight, I'm sharing from Morrison and Hirschfield, that basically looks at insulation ratio and permeable membrane. So basically, you can see here that the dark blue line has a very high perm ratio, high perm insulation and sheathing on the exterior, but a very low ratio, insulation ratio, which means that all of the insulation is on the interior and hardly anything on the exterior. So, and you can see that the red line that you see on the screen is the moisture content in the wall that you don't want to get to because that's going to have some potential consequences long term. And then by doing hydrothermal modeling, we can predict these. So you can see that when you don't have enough insulation on the outside, even if you put a more permeable membrane, which is basically the blue line versus the solid blue line versus the dotted blue line, you're still going to get condensation occurring in walls because you don't have enough R value on the exterior. And then if you increase your insulation ratio. So if you put more insulation on the exterior and less on the interior, you can see that regardless of the vapor permeance of that exterior insulation, they're all going to be very good. They're all going to be below that red line where the risk of condensation could occur. And it gets better when the insulation ratio gets better. So R value is what's driving condensation as opposed to vapor permeance of the outer layer. And there are some recommended values for different design temperatures, depending on indoor relative humidity and outdoor temperature. But in reality, what we're trying to show here is that you want to have at least 50 to 60% of your R value on the exterior of the wall, and then the remaining on the interior. If you have that ratio, that balance, that wall cavity is going to be warm enough that it'll water vapor moving through it will not reach its dew point, will not condense, and it'll just make its way up. And so split insulated assemblies work. We just have to make sure that we're managing the right ratios depending on the relative humidity of the environment that we're designing and the outdoor temperatures. So if we look at cladding attachments, we saw the importance of cladding attachments and the impact that it has on overall effective R value or U value of a system, of an enclosure system, and that kind of the best options are to move towards thermally isolated clips, or if we could screw the attach the metal cladding directly through the insulation. So even when we're using thermally isolated clips, so here's an example of a product that's available in Eastern Canada, thermally isolated clips. And you can see, so again, if I'm trying to reach an effective system R value of 23, based on the calculation and the information that is provided by the manufacturer of this attachment clip, with 6 inches of exterior insulation with a nominal R value of 25.2, basically, I would need 6 inches to get to an effective R23. So even if I use thermally isolated clips, if I don't insulate the inside of the backup wall cavity, I'm still looking at 5, 6 to 7 inches of exterior insulation. The minute we start adding insulation in the backup wall, the thickness required on the exterior goes down by about 50%. So it gets cut in half. So when we're considering attaching the cladding through the insulation, that's the option that provides us or allows us to retain almost 100% of the insulation nominal R value on the exterior because there's minimal thermal bridges. And so this is something that should be considered if you can do it. Because obviously it provides, it helps you meet the effective R value required with the least amount of insulation on the exterior. And so what's important to remember if you're considering this type of attachment method is to make sure you're using the insulation that has a high enough compressive strength that is specifically designed for those types of applications where it has enough compressive strength to transfer the loads, the dead loads and the wind loads of the cladding through the insulation through the screws into the backup wall. So there are different products that are on the marketplace that have been designed to allow this to be done, and their compressive strength is designed for different types of cladding weights. So for low, medium, and high cladding weights. So what's important is to make sure you're using the right one so that it can transfer the load through the insulation to the backup wall. And again, so we looked at how to optimize effective thermal resistance, or how to achieve high effective thermal resistance and the overall U value to meet the new energy efficiency requirements of the building codes. For the opaque area, but if we're looking at overall heat loss and how to improve that, or heat flow through buildings, how to minimize that. So one of the other things to consider is optimization at the window transition. So as an example here, you can see, and this is information coming out of the Morrison Hirschfield Thermal Bridge Guide, which I'll show you in a couple of slides, but basically just changing the alignment of the window, so putting it in line with the insulation as opposed to scenario A, you can see that the heat flow coefficient changes and improves when you align the window with the insulation, and you minimize the thermal bridge at the junction around the window opening. So little details like that make a big difference. And if you're using the NECB 2017, that you have to account for these when you're trying to show compliance to the minimum U value prescribed, or the effective thermal resistance prescribed, you're going to have to put these into your calculations. So you want to make sure that you're optimizing. Optimization details at parapets. And again, depending on the way the parapet is built and that junction, that transition between the parapet, the roof, and the wall, it has a significant impact on heat flow. And so if you design it with thermally isolated junctions that are better than just a standard junction, again, you can reduce the heat flow there, and it'll improve your overall effective thermal resistance. And then the optimization at the base of the wall. So again, if you insulate that concrete all the way up, even the portion above grade, you're minimizing that thermal bridge at the top of the wall. Again, you're reducing your heat flow, and you're going to improve your overall effective thermal resistance. Slab edge details, balconies. So again, those are weak points. That's where there's a lot of heat transfer in buildings. And so if we can incorporate some innovative details there, or thermally isolated junctions, it could significantly improve the overall U value of the opaque assembly. So some guides and tools to help you design and meet the new energy, design buildings and meet the new energy code requirements. There is the Morris and Hirschfield Building Envelope Thermal Bridging Guide, which is available on the BC Hydro website. So this is a guide that has many details in terms of opaque assemblies for both walls, roofs, foundation walls. It's got junction details, it's got slab edge details, connection details, window opening details, to help you really minimize heat flow throughout all of those areas. There are manufacturer guides as well that are specific to their products that you might want to look up or consider looking up. And then there are some good guides to low thermal energy demand for large buildings, again, from BC Housing. That's all available on their website. NAMA Canada, which is the North American Insulation Manufacturers Association, also has a guide to net zero for residential buildings. And it shows you some key details that you could incorporate in your designs to help you minimize energy consumption and energy demand. Oops. There are also some good technical documents that talk about the benefits of split insulated wall assemblies and the impact of insulating the backup wall on the amount of insulation required on the exterior wall of the wall, sorry. And then there's a good guide from RDH, a complete guide, and these versions get updated as new testing gets completed. And it's a cladding attachment guide for exterior insulated commercial walls that walks you through a series of different cladding attachment types and strategies, kind of similar to what I just reviewed. Some of the images from my presentation are coming out of this guide. So it's a very complete guide, and I strongly recommend you download it to help you with your future projects. There's also a MERB design guide that was just came out of Carleton University, which can easily be accessible. And then there's the effective thermal resistance worksheet that's available on the BC Hydro guide. So basically, this is an Excel sheet that allows you to calculate the effective R value of your overall opaque area to show compliance, or to demonstrate compliance for the prescriptive requirements in the 2017 National Energy Code for Buildings, where you need to include the heat flow through the junctions. So basically, it uses all of the calculations coming out of the Building Envelope Thermal Bridge Guide. And then in this Excel spreadsheet, all you need to do is enter the units in terms of either area or lineal feet of perimeter, and then look up the thermal transmittance value or the heat flow value you enter into the spreadsheet, and it automatically calculates the overall effective thermal resistance. So here's an example, just quickly. If we look at a mid-rise building, so the first thing you would do is you would identify your clear field assemblies, your opaque assemblies. So all the assemblies that are insulated differently. So in this example, we've got wall area 1 and wall area 2. Then you would go to the guide and you would look up the detail that is closest or representative of the way you've insulated those areas. And basically it'll tell you, give you a U value for that assembly. And then once you have the U value of those assemblies, all you need to do is calculate the areas for those that are representative of the way you've insulated those areas. You come back into the Excel spreadsheet and you basically enter the area for those assemblies as well as your transmittance value, your U value, basically, that you've looked up in the thermal bridge guide. So now that's the first thing that you need to enter. So now you've taken care of the clear fields. Now you got to look up, you got to do the same thing for the junctions. So basically, what are the junctions? There's a parapet to wall junction. There's a slab edge or a balcony junction. Here's a canopy junction. There's the junctions of the window openings to the opaque assembly. There's junctions at corners, junctions at bottom of walls. And then there's also penetrations through the envelope, like columns or beams. So once you've identified those, in each of the cases, you would look up the calculated heat flow in the thermal bridge guide, determine the length of that specific detail you're trying to evaluate. So in this case, as an example, my parapet, my roof to wall interface is 54 meters in length. I go into the thermal bridge guide, I look up the detail, and I figure out a heat flow, a lineal heat flow that is already given to us in the guide. And then all I do is I lay those two informations into my Excel worksheet, and it'll automatically start adding those up to calculate the overall effective thermal resistance. And I keep doing the same thing for all the other junctions. So intermediate floors, I add up all of the length that is representative of that intermediate floor detail. I look up the actual heat flow value in the thermal bridge guide, which is given to us in watt per meter Kelvin. And again, I'm going to transfer those into the Excel worksheet. Same thing for balconies. I figure my length, total length of balconies. I look up my detail, figure out my heat flow coefficient for that detail. Window perimeters, I add up all of the window perimeters. I figure out my length, total length. Go back to the thermal bridge guide, and I look up the detail that I am designing in my wall assembly. I look at the heat flow factor, and again, lay those into the Excel spreadsheet. And then finally, some additional transmittances, corners, as well as point loads. So like columns, so I determine how many of those I have and what the heat flow values calculated through those are from the thermal bridge guide. And again, I come back to the Excel spreadsheet. I'm entering either area or length for each one of the components. And then I'm entering U value or thermal transmittance in the appropriate column. And the spreadsheet automatically calculates the effective R value for the opaque assembly, including all of the junctions and the clear field details. And that's going to allow me to check the box to see whether I meet the prescriptive requirement in the NECP 2017 for the opaque assembly. And what's also neat about this spreadsheet is that it tells you what percentage of your heat flow is happening where. So you can see where the weak spots are or where your weak spots are and kind of look at ways to improve them. And as you improve them, your overall effective R value obviously gets better. There's also a neat little calculator that's available if you're working on buildings in BC, where you have to meet the various paths of energy compliance. There's this online virtual tool that's called Building Pathfinder that basically allows you to, based on your climate zone, you determine the shape of your building, the R value of your wall, the window U value, your window solar heat gain coefficient, the type of heat recovery that you have and their efficiency, the infiltration rate. And then based on all those choices, it'll tell you what your heat demand is for different units, depending on what level of performance you're trying to adhere to in BC, as an example. There, so a very good tool, a visual tool to kind of help you determine the impact of the choices that you make on the different parameters that have an influence on the overall heat demand per year. And that is the end of the presentation on addressing thermal bridges and exterior wall assemblies. So I wanted to thank you for attending today, and now we'll open it up for questions. So thank you very much, and we'll open it up for questions. Yes, I see the first question. So are there more challenges in Ontario's climate change versus BC's climate? I mean, that's a good question. It obviously, when you're in climate zones that have higher heating degree days, it's probably a little bit more onerous on the amount of energy efficiency that needs to be put in place. But I think the challenges are really more with respect to applying the details, and I would say it's about the same. I think I would say the only difference is really the amount of let's say insulation and energy efficiency measures that are required, but the challenges to me would be the same. And would you have any suggestions on further guides or tools? Yeah, I mean, that's obviously a great question. BC Hydro, that's a great point. Every time assembly get assembly performance, it gets updated. I believe it's of every 3 years. There's 100 details there, junction details, opaque value details. There's it's a good starting point. The Excel spreadsheet allows you to manipulate or try different solutions and then see what the impact is from an overall effective thermal resistance perspective. That's a good starting point. And then as you continue to search on that site, it provides access to additional guides. But that's a good starting point. If I could, that's what I would recommend. I work outside of BC, yeah, in the Arctic. I'm not aware of guides for the Arctic, but that's a good question. I know there's guides. Every province is going to be developing guides. I know BC have started because they took a leadership role with their energy step codes that have been introduced now for was it 3, 4, 5 years. As the rest of Canada catches up, I think the provinces will be developing guides to help the industry be able to implement the best practices in order to achieve the target, the intended target. So if it's not available yet, I'm not aware of guides for the Arctic. I know Natural Resources Canada are working on several guides and projects to help all of the regions meet or bump up their energy efficiency designs, but you'd have to stay tuned. I'm assuming all of the other provinces are going to catch up with their guides as they start adopting these new requirements. Yeah, thank you for your question. Yes, Owens Corning. So we have a dedicated technical support team for the architectural design community, as well as builders, contractors, customers right across Canada. So I'm in Eastern Canada, Quebec, and Atlantic Canada. We have my colleague Ernie Lee in Ontario and my colleague Louis Ferrier in Western Canada. So you could always reach out to us, and we'd be more than happy to provide all the support that we can that you would require there. So yes, we do offer the architectural services team, which is my team, offers that service right across Canada. Thank you for asking. Thank you very much, and thanks for everybody for participating. Thank you very much.
Yes, thank you for everyone who came and joined us live. Always makes me happy. All right, everyone, have a wonderful afternoon.
Thank you. Have a great day.
Thank you.
Bye.